What if the key to unlocking the secrets of the cosmos and the future of humanity lies not within the boundaries of our own planet, nor in the distant stars, but in the hidden corners of our solar system and beyond? Our documentary embarks on an awe-inspiring journey, weaving through 4 captivating themes that challenge our understanding of life, exploration, and our place in the universe. Our voyage commences with the tumultuous landscapes of Io, a world where fire and fury reign supreme. This moon, unlike any other in the solar system, is a testament to the dynamic and chaotic forces of nature. With hundreds of active volcanoes painting its surface, Io's relentless activity raises profound questions about the forces shaping the cosmos. As NASA's Juno spacecraft dares to venture close, we're left to ponder, what secrets does Io's fiery inferno conceal about the nature of our solar system? Next, we set our sights on Titan, Saturn's largest moon, a world where the script of life's possibilities is rewritten. Titan's dense atmosphere and liquid methane lakes present a stark contrast to the fiery visage of Io, offering a glimpse into the diverse conditions under which life could theoretically thrive. This segment explores the enigmatic beauty of Titan, posing the intriguing question: could this distant moon serve as a blueprint for life beyond Earth, challenging our definition of habitability? The narrative then shifts to Europa, Jupiter's icy moon, where beneath a frozen exterior lies the promise of unfathomed secrets. The James Webb Space Telescope's discovery of carbon dioxide on Europa's surface hints at the moon's potential to harbor life, challenging us to rethink our search for extraterrestrial existence. This revelation invites viewers to dive deep into the mysteries of Europa, contemplating the implications of its hidden oceans and the tantalizing possibility of life in its depths. Finally, we venture into the realm of exomoons, the hidden giants of the cosmos. These celestial bodies, Earth-sized and teeming with potential, represent the frontiers of our quest for life beyond our solar system. The exploration of exomoons suggests that these distant worlds could be the cradles of life, far more so than the exoplanets we've discovered thus far. This closing theme beckons us to consider the future of space exploration and the role exomoons might play in humanity's quest to find our place in the universe. Through the lens of Io's volcanoes, Titan's methane lakes, Europa's icy ocean, and the vast potential of exomoons, we explore the breadth of the cosmos, seeking answers and inspiring questions about the future of humanity in the vast expanse of space. Amidst the peace and tranquility of the celestial bodies of the solar system, there is one object that greatly disturbs the peace of the rest: the moon, Io. Unlike any other orbiting the mighty Jupiter, shrouded in mystery, Io is a world of fire and fury, a stark contrast to the icy moons and calm planets that share its cosmic neighborhood. This mysterious moon, the most volcanic body in our solar system, is a testament to the dynamic forces at work in the cosmos. Its surface, riddled with hundreds of active volcanoes, tells the story of the relentlessly complex gravitational pull of Jupiter and other moons. Meet Juno, NASA's intrepid explorer, on a journey to this fiery world. Its mission is to unravel the mysteries of Io, capture its fiery essence, and uncover the secrets that have long lurked beneath its tumultuous surface. As Juno makes its closest approach in 2 decades, we stand on the threshold of new discoveries and are ready to unravel the mysteries of this volcanic moon. What will Juno tell us about Io's turbulent volcanoes? How does the turbulent nature of this moon affect giant Jupiter and its other moons? And what can Io tell us about the forces that shape our solar system? Let's find out. Discovering new space vistas, Juno, a spacecraft made not only of metal and circuitry but also of ambition and curiosity, is embarking on a journey that hasn't been taken in more than 2 decades. For the first time in 20 years, a spacecraft dares to come so close to Io that we can come face to face with a world of extreme volcanic activity. Juno's close approach is not just a routine flyby, but a bold dive into the unknown. The spacecraft, equipped with state-of-the-art instruments, is designed to withstand the harsh radiation environment of Jupiter and its moons. As it approaches the rough surface of Io at a distance of 930 miles, Juno's sensors come to life, taking high-resolution images and collecting valuable data. In late 2023, the probe made its closest flyby of Io, taking some incredible images in the process. In them, Jupiter's moon appears to glisten with sulfuric hues, and its surface is speckled with spots created by the ongoing volcanic activity that rages on it. By combining data from this flyby with our previous observations, the Juno science team is studying how Io's volcanoes vary, says astronomer Scott Bolton of the Southwest Research Institute. We are looking for how often they erupt, how bright and how hot they are, how the shape of the lava flow changes, and how Io's activity is connected to the flow of charged particles in Jupiter's magnetosphere. The heart of this mission lies in the technological prowess that Juno possesses. The spacecraft's JunoCam continues to take spectacular images despite the challenges of Jupiter's intense radiation. The Stellar Reference Unit's Stellar Navigation Camera is also a scientific instrument, providing the highest resolution images of Io's surface to date. On Earth, scientists are studying the data coming from Juno. Each byte of data is a piece of the puzzle, revealing new information about the volcanic nature of Io. Analyzing this is a window into our solar system's past, present, and future. So, late last year, NASA's Juno probe took the highest resolution images of this moon to date. Among these images, one that stands out is one taken on December 30th, which vividly depicts the volcanic nature of Io. This image, enhanced to emphasize details, shows a volcanic plume erupting from Io's surface, with plumes reaching more than 60 miles. Given that the moon's diameter is about 2,200 miles. As Juno continues its journey around Jupiter, each orbit brings new opportunities, new challenges, and new discoveries. Among the planet's other 95 moons, Io stands out not only for its proximity to Jupiter, but also for the dramatic geologic activity that this proximity provokes. The volcanic nature of the moon is a direct consequence of Jupiter's enormous gravitational forces. Io is not a huge moon. It's only slightly larger than the one orbiting our planet. However, as the largest planet in our solar system, Jupiter has tremendous gravity. This enormous force stretches and squeezes Io, creating what is known as tidal heating. The satellite's orbit itself is not a perfect circle, resembling more of an ellipse, so the moon experiences varying degrees of gravitational pull from Jupiter. As it approaches Jupiter, the planet's gravity stretches Io, and as it moves away, it compresses it. This constant stretching creates tremendous internal heat within Io, leading to its intense volcanic activity. This JunoCam image captures a plume of material ejected from the unseen volcanic Prometheus. Indicated by the red arrow, the plume is just visible in the darkness below the terminator, the line dividing day and night. The image was taken by spacecraft on October 15, 2023. Tidal heating is so intense that it turns Io's interior into a bubbling cauldron of molten rock. This heat leads to the volcanic activity that defines Io's landscape. Hundreds of volcanoes dot its surface, some of them spewing lava fountains up to hundreds of kilometers high. There are about 400 active volcanoes on Io, about 150 of which are erupting at any given time. But Jupiter is not the only player in this gravitational confrontation. The other Galilean moons, Europa, Ganymede, and Callisto, also exert their influence on Io. Their gravitational attraction helps to maintain Io's elliptical orbit, thus playing a crucial role in the tidal heating process. This complex gravitational interaction is a perfect example of how celestial mechanics determine the fate of a moon. The tidal forces of Jupiter and its moons don't just heat Io, they create a world in which geologic activity is the norm, not the exception. Io, a moon shrouded in fire and brimstone, plays a key role in the grand theater of Jupiter's system. Its incessant volcanic activity not only shapes the landscape, but also significantly affects the very nature of Jupiter's magnetosphere. As we mentioned earlier, the volcanoes on this satellite are the most active in the solar system. In doing so, they spew huge amounts of sulfur dioxide, or SO2, into space. This outgassing, a direct result of intense internal heating, contributes to an atmosphere rich in sulfur compounds. But Io's influence extends far beyond its own atmosphere. As Io rotates within Jupiter's massive magnetosphere, sulfur dioxide and other volcanic gases ionize, becoming charged particles. These particles become trapped in Jupiter's magnetic field, forming a plasma torus along Io's orbit. This torus, a glowing ring of ionized particles, is a direct manifestation of the moon's volcanic power. The plasma torus is not a static feature. It changes in response to Io's volcanic activity. The ejection of material from volcanoes feeds the torus, affecting its density and composition. This complex interaction between Io's volcanism and the plasma torus illustrates the interconnectedness of Jupiter's system. It's also thought to be responsible for powerful, permanent auroras at the planet's poles. Volcanic emissions, once in the atmosphere, escape into space. Here they undergo rapid reneutralization, a process that ejects these particles at high velocity in a plane perpendicular to the local magnetic field. This phenomenon continues to the formation of extended sodium nebulae, adding another layer to the complex environment around Jupiter. Observational studies have been crucial in shedding light on these interactions. For many years, telescopes, like TRAPPIST, have followed the variability of Io's sodium cloud. These observations have shown that the physical properties of the sodium jets from Io are highly variable and, interestingly, do not always correlate directly with the global brightening of Jupiter's plasma torus or the extended sodium nebula. This study highlights the complexity of the surface-atmosphere-magnetosphere coupling in the Jupiter system. Current research aims to reveal the precise mechanisms by which Io's volcanoes supply material to the plasma torus, and how Io's sodium jet contributes to filling the plasma reservoirs of the magnetosphere. Thus, Io's relentless volcanic activity and its interaction with Jupiter's magnetic fields are not just isolated phenomena. They play a fundamental role in shaping the dynamics of Jupiter's magnetosphere, producing plasma structures and neutron clouds that are key to understanding the complexities of planetary magnetospheres. Ongoing research and observations allow us to separate the layers of these interactions, offering a deeper understanding of the workings of our solar system. As we look to the future of space exploration, the fiery moon Io appears as a beacon of mystery and potential. The next phase of Io exploration is poised to reveal secrets that have remained hidden beneath its stormy surface for centuries. Introducing the Jupiter Icy Moons Explorer mission, abbreviated as JUICE. JUICE aims to study Jupiter's icy moons, offering intriguing opportunities to further our understanding of Io. Although JUICE's primary focus is on Ganymede, Europa, and Callisto, its extensive suite of instruments can provide valuable insights into Io's dynamic environment. The interplanetary spacecraft was launched on April 14, 2023, from the Guiana Space Center in French Guiana by the European Space Agency. The spacecraft is expected to reach Jupiter in July 2031 after 4 gravity assists and an 8-year journey. As JUICE passes through the Jupiter system, its trajectory may provide opportunities to observe Io. These encounters may provide additional data on the satellite's volcanic activity and its effect on Jupiter's magnetosphere, complementing the conclusions drawn by missions directly targeting Io. Equipped with sophisticated instruments designed to study magnetic fields, plasma environment, and atmospheric composition, JUICE has the potential to indirectly expand our knowledge of Io. By studying Jupiter's magnetosphere and the interactions within it, JUICE can provide a broader context for the satellite's role in the entire Jupiter system. Another mission, Io Volcano Observer, or IVO, is a bold initiative that represents the next leap in our quest to understand this volcanic moon. IVO is a proposed mission designed to study Io's intense volcanic activity, its subsurface structures, and the complex processes that drive its geologic dynamism. IVO's mission is to enter orbit around Io and make multiple close flybys. Equipped with state-of-the-art instruments, IVO will map Io's volcanic heat flows, study lava composition, and probe the moon's internal structure. This mission aims to answer fundamental questions about the mechanisms of volcanism on Io and the role of tidal heating in its activity. One of the most interesting aspects of the IVO mission is exploring the bowels of the moon. What lies beneath its fiery facade? IVO seeks to shed light on this mystery by studying the moon's internal structure. Seismic measurements and magnetic field analysis may reveal the presence of subsurface magma chambers and provide insight into the moon's volcanic flow system. The potential for new discoveries about Io's volcanic mechanisms is enormous. IVO observations could revolutionize our understanding of volcanic processes, not only on Io, but throughout the solar system. By studying Io's unique volcanism, we'll be able to gain insight into the thermal evolution of planetary bodies and the role of tidal forces in shaping planetary geology. In the meantime, Juno continues to work, with many more observations planned, not only of Io, but also of the other Galilean moons, and, of course, Jupiter itself. The spacecraft will continue to operate until September 2025, or until it breaks down, whichever comes first. In the meantime, we'll look forward to more images taken by the next flyby. Humanity stands on the threshold of a new era, an era defined not only by exploration, but also by the bold dream of colonization. For decades, our gaze has been fixed on the familiar, the moon, our celestial neighbor, and Mars, the red beacon in our night sky. These worlds, once the subject of science fiction, now beckon us with the promise of new frontiers. But beyond these well-trodden paths lies a world shrouded in mystery, a world that's changing our understanding of what it means to be a moon. This is Titan, Saturn's largest satellite. Titan is a world covered with a dense atmosphere, which is rare for a moon. It's a place where rivers and lakes flow not with water, but with liquid methane and ethane. Here, the sky is raining gasoline, and the cold is beyond anything that can be experienced on Earth. Yet, in this alien landscape lurks the potential for something extraordinary. Could Titan, a world so unlike our own, hold the key to our future in space? Could this distant moon hold the secrets to not only surviving, but thriving beyond our home planet?
It's one small step for man, one giant leap for mankind.
As we turn the pages of our history of space exploration, the Moon and Mars become beacons of human ambition. The Moon, our nearest celestial neighbor, has always been a constant companion in our night sky, a symbol of our desire to leave the confines of the planet. Mars, in turn, with its striking resemblance to Earth, fuels our dreams of finding a new home in space. Nevertheless, the Moon, despite its proximity, presents serious problems. Its surface is a barren wasteland, devoid of atmosphere and offering no protection from the harshness of space. The lunar environment is a vacuum, exposing astronauts to extreme temperatures and cosmic radiation. No atmosphere means no air to breathe, no wind to carry sound, and no sky to protect against the relentless barrage of solar and cosmic rays. Mars, though more Earth-like, is not without its own problems. Its thin atmosphere, consisting mostly of carbon dioxide, offers little protection from solar and cosmic radiation. The Martian environment is harsh and merciless, and temperatures at the poles can drop to minus 257 degrees Fahrenheit. The lack of a global magnetic field exposes the surface to the full force of the solar wind and cosmic rays. In contrast, Titan, Saturn's largest satellite, presents a very different environment. Shrouded in a dense atmosphere, Titan offers a natural barrier against the dangers of cosmic radiation. This atmosphere, richer in nitrogen than even the Earth's atmosphere, is the key to protecting future colonists from cosmic rays that mercilessly bombard less protected worlds such as the Moon and Mars. Titan's atmosphere isn't just a shield, it's a gateway to opportunity. Unlike the Moon and Mars, the air pressure on Titan's surface is 1.5 times higher than on Earth, creating a surprisingly familiar pressure environment for human explorers. This dense atmosphere opens up new possibilities for exploration and colonization, possibilities that are beyond the reach of our more trivial space goals. As we rethink our goals for space colonization, Titan becomes a compelling alternative, a world in which the atmospheric and radiation problems that limit our ambitions on the Moon and Mars become its strengths. Titan invites us to envision a future in which humanity can thrive under the protective embrace of an alien sky. A future in which the mysteries of this distant moon become stepping stones to our expansion into space. As we mentioned earlier, Titan, a moon of many mysteries, orbits around Saturn. Discovered in 1655 by Dutch astronomer Christian Huygens, Titan has captivated the imagination of scientists and dreamers ever since. This world is both similar to and in stark contrast to our Earth. Titan's environment is unlike anything else we've encountered in our solar system. It's the only known moon with a dense atmosphere, and the second largest moon in our solar system after Ganymede, a satellite of Jupiter. But it's not just the size that makes Titan stand out, it's the rich composition of its atmosphere and surface that really sets it apart. This moon is surrounded by a thick, nitrogen-rich atmosphere, similar in composition to Earth's, but far denser and more extensive. It's permeated with organic molecules, creating a kind of hazy orange glow that obscures the surface of the satellite from view. It's this nitrogen-dominated atmosphere that provides protection from solar radiation, which contrasts sharply with the barren sky of the Moon and Mars. Beneath this alien sky lies a landscape at once familiar and utterly alien. Titan's surface is formed by rivers and lakes, but they're not bodies of water as we know them. Instead, they're filled with liquid methane and ethane, flowing through channels carved into the Moon's icy crust. These hydrocarbon seas are a true marvel, a testament to the diversity of the universe's chemistry. The presence of these surface fluids is a key characteristic that distinguishes Titan from other celestial bodies. On Earth, the water cycle shapes climate and geography. On Titan, a similar cycle occurs, but the role of water is played by methane and ethane. This hydrocarbon cycle, with methane rain and ethane lakes, creates a dynamic environment that may provide clues to understanding the complexity of planetary atmospheres. So, by breaking the limits of our standard perception, we're slowly uncovering exactly what makes a planet or moon habitable. Its nitrogen-rich atmosphere and surface fluids open the door to new possibilities. Let's find out what they are. So the Moon's nitrogen-rich atmosphere provides a natural barrier against cosmic radiation, a major challenge for space colonization. Why do we pay so much attention to solar radiation? Well, the answer is simple, yet profoundly important. Solar radiation is a ruthless destroyer of living cells. It doesn't just affect microscopic life forms, it directly affects us as human beings. Unshielded exposure to solar radiation can cause severe cellular damage, destroying the very fabric of our biological existence. In space, spreading uncontrollably, this radiation poses one of the greatest threats to the survival and health of astronauts. On Earth, it's the atmosphere and magnetic field that protect us. On Titan, it's the dense nitrogen atmosphere that provides vital protection, making it a safer haven for future human colonists than the barren landscapes of the Moon or Mars. Beneath this protective dome is a world of liquid methane and ethane. These hydrocarbon lakes and rivers stand in stark contrast to the bodies of water we know on Earth, yet they offer intriguing possibilities. Imagine a world where boats sail on methane seas, where the familiar concept of the liquid cycle takes on a whole new form. The presence of these surface fluids is not just a curiosity, it's a resource. Methane and ethane have the potential to be used as fuel, providing energy for future colonies. This abundance of hydrocarbons makes Titan an attractive target for colonization, offering a solution to one of the biggest problems of space habitation: sustainable energy sources. But Titan's gifts don't end there. Beneath its icy surface lies another treasure: water ice. The very water so essential to human life is abundant on the satellite, trapped in its frozen crust. The presence of water ice, along with hydrocarbons, makes this moon a repository of vital resources, setting the stage for a self-sustaining human presence away from Earth. Titan, a world of incalculable potential, also presents enormous challenges. Severe cold, during which temperatures drop to -356 degrees Fahrenheit, creates an environment unsuitable for human life as we know it. In turn, methane rain, a phenomenon unique to this moon, adds another layer of complexity to the survival equation. To overcome these challenges, we must turn to the pinnacle of human ingenuity and technology. Colonizing Titan will require not just adaptation, but a complete rethinking of human habitation in extreme conditions. Imagine dwellings designed to withstand low temperatures, insulated with materials yet to be invented, and harnessing the power of Titan's own resources to provide warmth and comfort. These habitats could be equipped with systems to convert atmospheric methane into heat, turning the problem itself into a resource for solving it. But survival is more than just keeping warm. Methane rain, while an obstacle, could turn into an advantage. Advanced collection and filtration systems could recycle methane not only as an energy source, but also as a raw material for essential commodities. Now, let's imagine a human colony on Titan. Imagine domed cities, their architecture a blend of science and art, designed to harmonize with Titan's unique environment. These structures, resistant to cold and methane rains, would be interconnected, forming a network, demonstrating human resilience in the face of alien conditions. Inside these domes, life thrives. Hydroponic gardens provide food, recycling systems conserve resources, and public areas foster a sense of community. It's a place where humanity has not just survived, but flourished, adapting decisively to Titan's challenges. Colonizing Titan is not just a distant dream. It's a future that beckons us to take up the challenge. With each technological breakthrough, with each bold leap of imagination, we come closer to making this alien world a new home for humanity. Watching the thriving human colony on Titan, it becomes clear that this moon is more than just a new home for humanity. It's a center of economic and scientific opportunity. The unique environment and abundant resources offer unprecedented prospects for both. The economic benefits of colonizing Titan are rooted in its vast hydrocarbon reserves. Key components of Titan's lakes and atmosphere are not only potential sources of energy, but also valuable raw materials for chemical synthesis. The ability to harness these resources could turn Titan into an economic center, meeting both the colony's needs and potentially supplying materials for interplanetary trade. Scientifically, Titan is a gold mine. Its complex atmosphere and surface chemistry offer unique research opportunities that offer insights into organic chemistry and astrobiology. Studying Titan's methane cycle and its prebiotic chemistry could unlock the secrets of the origin of life, not only on Earth, but potentially throughout the cosmos. Moreover, Titan's position in the solar system and its resources make it an ideal launching pad for future space exploration. Its low gravity and abundant fuel reserves could make it easier to launch spacecraft to distant destinations, making Titan a strategic outpost for exploring the outer solar system and beyond. However, with these opportunities come important ethical considerations. As we embark on the colonization of Titan, we must reflect on our responsibilities in interacting with the new world. Conservation of Titan's environment, respect for its unique characteristics, and thoughtful stewardship are paramount. We must approach Titan not as conquerors, but as custodians. How we relate to this world in the future will reflect our values and our ability to balance progress and responsibility. As we conclude our journey, let's reflect on the key points. A moon once shrouded in mystery has turned out to be a world full of potential. We explored the protective properties of Titan's nitrogen-rich atmosphere, a natural shield against the dangers of cosmic radiation. We traveled through alien landscapes where rivers and lakes of methane and ethane cut through icy terrain, offering resources that could secure our future in space. Our journey also took us to the potential of a vibrant human habitat, where ingenuity and resilience have turned challenges into opportunities. We saw how Titan's economy, driven by its abundant resources, can be a cornerstone of our interplanetary endeavors. As we ponder the future of humanity on Titan, we're reminded that colonization is not just about achieving technological perfection. It's a journey that forces us to grow, learn, and respect the universe we live in. So we leave you with a great question. What does this step mean for the future of humanity? How will our efforts on this distant moon affect our destiny in the vast, uncharted expanse of space? In the field of space exploration, the James Webb Space Telescope is a beacon of human ingenuity and curiosity. Its recent incursion into the depths of our solar system has revealed discoveries that challenge the possibility of life beyond Earth. Among the many celestial bodies orbiting our giant neighbor Jupiter, Europa is a world of special interest. With its jagged surface and hidden ocean, this icy moon has long intrigued scientists and dreamers alike. However, it's the recent discovery of JWST that's brought Europa into the spotlight of astrobiological research. JWST, in an unprecedented observation of the Moon, has discovered carbon dioxide on Europa's surface. This discovery, while seemingly simple, has profound implications. Carbon dioxide, a molecule integral to life as we know it here on Earth, could be a marker pointing to the potential for life on extraterrestrial worlds. Let us together delve into the data obtained by JWST. What secrets does Europa hide beneath its icy facade? Could the discovery of carbon dioxide be a clue to life beyond Earth? Europa, a moon full of mystery, is a landscape both alien and fascinating. Its surface is covered in a canvas of ice with a complex network of lines and ridges. These features, known as lineae, are not just surface scars, but tell the story of the dynamic geologic processes taking place. This 9 to 15 mile thick ice shell hides a vast ocean that has interested scientists for decades. The lines on Europa's surface are believed to be the result of the ice crust interacting with the moon's underground ocean. These cracks and ridges form as the ice shifts and breaks, a process driven by Europa's motion around Jupiter. Beneath this frozen barrier is a salty ocean, estimated to be 40 to 90 miles deep. This hidden sea, dark and cold, is kept liquid not by solar heat, but by Jupiter's immense gravitational pull, so-called tidal deformations. The satellite rotates around its giant parent and generates enough heat to maintain the ocean's liquid state. The chemical composition of this ocean is the subject of intense research and speculation. It's believed that there may be hydrothermal vents on the ocean floor, similar to those found in Earth's oceans. These vents may provide the necessary energy and minerals to sustain life, making Europa's oceans a prime candidate for the search for extraterrestrial life. The physical properties of Europa's oceans also raise intriguing questions. The presence of salts and the ability to form complex organic compounds, combined with the energy of hydrothermal activity, create an environment in which life can exist. Ocean depths and pressures, although extreme, are not beyond habitability, as evidenced by life in the deep gorges on Earth. Europa's mysterious environment with its icy surface and ocean is an interesting case for research. But what exactly has attracted the eyes of scientists to this moon this time? With the help of JWST, astronomers have made an interesting discovery. Using data from NASA's Space Telescope, they've detected carbon dioxide on the icy surface of the satellite. This discovery is not just an addition to Europa's chemical profile, it's an important key to understanding the moon's potential for life. Using the near-spec near-infrared spectrograph, JWST has discovered carbon dioxide in the geologically young and chaotic Terra Regio locality. This discovery is not just about the presence of a molecule, it's about its origin. The carbon dioxide on the surface of Europa is thought to have come from within, from its mysterious underground ocean, rather than having been deposited by external forces, such as meteorites. This discovery suggests a dynamic exchange between Europa's ocean and its icy shell. The most interesting thing here is that carbon dioxide is unstable on Europa's surface, suggesting constant replenishment from the moon's interior. The presence of carbon dioxide in the young terrain region indicates a recent and possibly ongoing process. This exchange may hold the key to understanding ocean chemistry and, by extension, its ability to support life. This discovery was made possible by the near-spec JWST instrument, which provided detailed spectra of Europa's surface. The ability to pinpoint the location of specific chemicals, such as carbon dioxide, allows astronomers to build a more complete picture of Europa's chemical landscape. Each discovery adds a piece to the puzzle of this mysterious moon. But why is this gas being released? And even more so, how does this cosmic body remain warm, supporting a liquid subsurface ocean? Europa, in its gravitational interaction with Jupiter, experiences a phenomenon known as tidal deformation, or tidal flexing. This process, caused by Jupiter's enormous gravitational pull, is one of the key factors in shaping Europa's potential to harbor life. As Europa revolves around Jupiter, its shape is constantly bending. This constant bending generates significant internal heat, a process quite different from the solar heating that we're familiar with on Earth. This internal heating is critical because it's thought to keep Europa's underground ocean in a liquid state, despite the relatively low temperature of outer space. The heat generated by tidal bends may also stimulate geologic activity on Europa, such as subglacial volcanism and hydrothermal vents. These openings, if present, may be similar to those in Earth's deep oceans, which teem with life despite the lack of sunlight. The energy provided by tidal bends could be a crucial ingredient for life. In Earth's oceans, hydrothermal vents support entire ecosystems where life forms utilize chemical energy released from the Earth's interior. On Europa, a similar process could occur, with life forms potentially using the energy from hydrothermal vents to power their metabolic processes. In such an environment, life could exist independently of sunlight, relying instead on the chemical and thermal energy provided by Europa's internal dynamics. Carbon dioxide, a molecule so integral to life on Earth, now takes center stage in the discussion of extraterrestrial life. On our home planet, carbon dioxide is the cornerstone of the biological process of photosynthesis that drives Earth's ecosystems. But what role can this essential molecule play in the cold, alien environment of Europa? The discovery of carbon dioxide on Europa by the James Webb Space Telescope opens up intriguing possibilities. In extraterrestrial environments, especially on icy moons like Europa, carbon dioxide may play a different but equally important role in sustaining life. In the absence of sunlight, life in Europa's oceans will have to rely on chemical energy, a concept known as chemosynthesis. This is where carbon dioxide can play a key role. In Earth's deep oceans, some organisms use carbon dioxide, combined with hydrogen from hydrothermal vents, to create organic matter. This process, although independent of sunlight, is a fundamental aspect of life in extreme environments. The presence of carbon dioxide on Europa may indicate a similar process. If there are hydrothermal vents in Europa's oceans, as many scientists believe, these may be the very places where life forms use carbon dioxide, perhaps like Earth's deep-sea organisms. This leads to an intriguing question. Could the carbon dioxide on Europa's surface be a byproduct of biological activity in its oceans? While the topic remains speculative, such a possibility adds an exciting dimension to the search for life beyond Earth. The role of carbon dioxide in extraterrestrial biological processes is the subject of intense research and speculation. Its presence on an icy moon may be a marker indicating the potential for life in environments far removed from the sunlit world we know. So let's summarize. The key to Europa's potential habitability lies in three basic elements: liquid water, an energy source, and the necessary chemical elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Europa's subsurface ocean and the energy generated by tidal bends are consistent with the first 2 points, and the presence of carbon dioxide on its surface hints at the presence of the necessary elements. Detecting carbon dioxide on Europa is an important piece of the puzzle. On Earth, carbon dioxide is integral to life, playing a central role in photosynthesis and respiration. In the alien environment of Europa, this molecule may be equally important, potentially acting as a building block or part of metabolic processes for hypothetical life forms. The presence of carbon dioxide also suggests that Europa's environment is chemically active, a key factor in the search for life. This activity could indicate geologic processes or even hint at biological processes if life existed there. It's also only possible to emphasize the importance of studying Europa's ocean as a testing ground for understanding the origin of life. The conditions on Europa may be similar to those of early Earth, giving a rough idea of how life could have originated under extreme conditions. On Earth, carbon dioxide is a fundamental component of life, involved in processes such as photosynthesis and respiration. In the alien environment of Europa, this molecule could play a similar role, potentially serving as a building block for life or part of the metabolic processes of a life form. Carbon dioxide could be a byproduct of biological activity or a resource. As we stand on the threshold of a new era in astrobiology, the significance of the discoveries of the James Webb Space Telescope propels us into a future rich with possibilities. Upcoming missions to Europa, particularly the European Space Agency's JUICE, Jupiter Icy Moons Explorer, and NASA's Europa Clipper, are designed to broaden our horizons and deepen our understanding of this enigmatic moon. NASA's JUICE mission, launched on April 14, 2023, aims to make detailed observations of Jupiter and its 3 large icy satellites, with a particular focus on Ganymede. However, the Europa survey will provide important data that will complement JWST's findings by providing insight into Europa's icy crust and its subsurface ocean. In turn, NASA's Europa Clipper, scheduled for launch in October 2024, is designed specifically to study Europa. Equipped with a suite of sophisticated instruments, this mission will conduct a detailed reconnaissance of Europa's ice shell and subsurface ocean in search of signs of habitability. The purpose of these missions is to build on JWST's groundbreaking discoveries, delve into the mysteries of Europa's environment. By scrutinizing Europa's surface, analyzing its ocean, and searching for biochemical signatures, These missions will improve our understanding of this moon's potential to support life. By the way, you still have a unique opportunity to be part of this historic exploration and get into the history of this remarkable moon. To quote NASA, join the mission and have your name engraved on NASA's Europa Clipper spacecraft as it travels 1.8 billion miles to explore Europa, an ocean world that may support life. Sign your name today to the message in a bottle. End of quote. Just imagine at a time when some people haven't even visited the next country, a piece of your personal history will travel such distances to orbit another planet. A truly mesmerizing thought. By adding your name, you're not just leaving a personal mark, you're becoming part of a legacy that will resonate in the annals of space exploration. Europa, once a distant and icy moon, is now the center of our quest to understand the existence of life beyond Earth. The JWST results, combined with future JUICE and Europa Clipper studies, usher in a new era of astrobiology. An era in which the search for extraterrestrial life is moving from the realm of speculation to reality. The solar system has served as a reliable bulwark for life. But one day, humanity will have to leave its native Earth to continue existing. In recent decades, scientists have been desperately looking into the dim depths of space in search of a haven for life. So far, none of the exoplanets we've found have refuted the hypothesis of the uniqueness of life. But what if we're simply looking in the wrong place? Perhaps it's not the planets that hold all the answers, but their moons. In the mystical deep space, exomoons are unlike any other satellite in the solar system. The size of our Earth, these hidden giants have an amazing feature. Life can be found in their interior, many times more often than on ordinary exoplanets. Today, we'll dive into the mysterious, distant universe and try to discover why exomoons may someday change humanity. Let's go back to the very beginning of the history of exoplanet science. Since astronomy received a strong impetus only in the middle of the 20th century, scientists began to study the first exoplanets not so long ago. The first confirmed exoplanets were recorded in 1992. It was a group of Earth-mass planets orbiting the pulsar PSR B1257+12. Just 3 years later, scientists found the first planet orbiting the star 51 Pegasi, similar to our Sun. This was the birth of exoplanetary science, which is dedicated to the study of planetary systems outside our solar system, and, in addition, the search for places where human-like life could originate. Other exoplanets available in our visible universe didn't have to wait long either. In the following years, astronomers found several more exoplanets, until in 2009, the Kepler Space Telescope was sent to explore outer space. In just 5 years of operation, it was able to confirm about 715 exoplanets, with a size and conditions similar to Earth's. As of now, we already know about more than 5,500 planets outside the solar system, and the recently sent James Webb Telescope will likely to be able to show us even more distant planets. Further, in 2013, scientists were able to determine the planet's color for the first time, and a year later, they were able to record the magnetic field, and later, volcanic activity. Finally, in 2018, astronomers made a new, potentially breakthrough discovery. For the first time, a possible exomoon was recorded near the planet Kepler 1625b. While this may not seem like such an incredible discovery at first glance, exomoons open a new chapter in modern astronomy, not only as novel, hitherto unexplored space objects, but also as potential elements for supporting life on exoplanets and satellites themselves. Every year, knowledge about distant, dim exoplanets deepens, bringing scientists closer to a complete picture of the history of the entire universe. But how did the scientists manage to confirm so many planets in such a short time, when it's impossible to take a photo of each one? only 69 planets were found with images. The most popular method is the transit method, which you may already know. When an exoplanet passes by its central star, the same star becomes slightly dimmer, which reveals the presence of an object orbiting it. Although this method doesn't allow us to directly observe the planet, and may turn out to be just a glitch, it is currently the most effective of all. Exoplanet exploration plays a crucial role in all of astronomy and the future of all of humanity. Exomoons, as a new chapter in exoplanet science, may have great potential for the search for extraterrestrial life. However, despite this, exosatellites are of not much interest to current research. The main problem associated with the search for these exoplanets is their elusiveness to telescope radar. Although no scientists deny that some exoplanets may have satellites, it's an extremely difficult and, to some extent, even impossible task for our current technologies to investigate them. The transit method, or more precisely, the method of studying the shift in the spectrum of stars, can confirm an exoplanet. But a satellite orbiting it? Almost under no circumstances, unless, for example, the spacecraft is in the closest possible proximity to the object of observation due to a completely insignificant change in the brightness of the star. Thus, even the very first exomoon found by Kepler and the ones discovered later near the planets Kepler 1708b and Kepler 1513b are still not perceived as full-fledged proof of their existence, and therefore there is a possibility that it could be just some kind of technical error during the observation, which is not so far from the truth, since further observations did not yield any encouraging results. However, as in the case of the giant planet satellite Kepler 1625b, an exomoon can be seen if it is large enough. So far, the first hypothetical exomoon could be the size of the Earth and have a strange tilted orbit like Neptune's moon Triton. Such a huge size of a possible moon may become one of the most important elements in the further search for other moons. Thus, more than 20 exomoon candidates are currently known. All of them are gigantic. Probably at least for Kepler 1625b, it's the star around which it orbits. It is a red giant. This dying star can heat the moon's atmosphere, increasing its effective diameter and allowing scientists to detect satellites more often. However, perhaps right now, exomoons are not of too much scientific importance for scientists to invest a lot of resources in developing technologies to find them. At this stage of our science, exomoons don't seem to be a higher priority than other space objects, such as exoplanets. The satellites of distant planets are too complex to study and have a very high chance of a false positive result. Therefore, it may take months or even years of observation and analysis to confirm one satellite, when it seems more rational to spend this resource on exploring a planet with potential support for life, including human life. Of course, it is possible that exomoons may hide life in their interior, but alternatives in the form of rocky exoplanets like Earth are still of much higher importance in scientific circles. But we're going to focus on the exomoons themselves and try to investigate them. Is there any need to study these mysterious and hidden moons at all? In fact, these moons contain a lot of information for our complete understanding of the structure of the universe. But this will only be possible in the future, albeit not in the near future. The first thing that draws scientists' attention to even just candidates for exomoons is their size. The largest moon in the solar system, Ganymede, orbiting Jupiter, has a diameter of 3,273 miles, or 5,268 kilometers. But recorded exomoons can reach the size of the Earth, or even Neptune. Therefore, since such moons are even difficult to distinguish among exoplanets, it's incredibly exciting to imagine what moons might look like and what activity they exhibit. It's possible that some large exomoons have many of the features of planets, and that their study could overturn everything we know about satellites. Their similarities to other exoplanets, such as their likely geologic activity, bring us to the next important point for careful study in the future, and that is the support of life. We know that several moons of the solar system, such as Enceladus, or Europa, despite their low surface temperatures and small size, could, hypothetically, be a haven for living organisms due to the presence of global oceans. However, what about the much more massive moons, which not only can support a dense atmosphere, but also have more access to building chemicals, both from the inside and outside? According to a study by the University of Washington, exomoons have more potential to support life than even exoplanets. They also have a habitable zone, although it's slightly different. But the main argument for exomoons as one of the most intriguing places for life to exist is the availability of several heat sources for them. The first source is the star itself, and the second is their planet. The moons are heated by the gravitational pull of the planet, which keeps the probable water in the interior of the moon in a liquid state. Moreover, heating from an exoplanet can stimulate geological activity, such as volcanic eruptions, creating enough gas inside the moon to maintain an atmosphere for a long time, and also bringing various crucial chemical elements to the surface. So exomoons are not as simple as they may seem. Perhaps the difficulty of finding them will be rewarded with a potential breakthrough in science. Finally, exomoons may become the necessary tool to study the formation of our universe. Thus, the analysis of exomoons near different stars and planets can reveal to scientists how space objects are formed, what factors are responsible for supporting life, and what the history of other planetary systems is in general. In particular, comparing the moons of the solar system with those of distant systems can give scientists an understanding of the specifics and conditions of their development, as well as an approximate value of the abundance of systems where complex intelligent life has developed. The Earth, hypothetically, may be almost the only planet on which life could have formed, at least in the visible universe. And any clues on exomoons with potentially higher chances of supporting living organisms can confirm or deny this. However, for now, deep exploration of exomoons is only a matter of the future. On the other hand, the James Webb Space Telescope mission will continue for several more years, so perhaps the hope of finding an exomoon for the first time in this decade is not going away. Nevertheless, since the search for exomoons is an extremely difficult and almost impossible task for our current technologies, exomoons are likely to become one of the drivers of technological progress. As we know, the transit method or gravitational lensing will not help to look for microsigns of the presence of exomoons, so this factor is already challenging scientists to modify or even create new technologies to capture such subtle objects. But this is a task for the near future. In the long term, both intriguing moons and exoplanets will require much more thorough analysis, including using images and samples of the atmosphere or even soils. So, if interesting candidates where extraterrestrial life exists are ever found, then comprehensive space missions are likely to follow, advancing human knowledge of the research focus. The only step we have left to take is to find such an exoplanet or exomoon. In 2026, the European Space Agency plans to send the Plato mission, which will continuously look at several areas in outer space to capture transiting objects. The mission will last for 6 years and may be the one to make this expected discovery. However, the benefits of exomoon search and exploration do not end with a technological breakthrough. Exomoons are very valuable natural laboratories located near various planets and stars. Analyzing the impact of these bodies on the moons will not only deepen what's known about the formation of planets, but also demonstrate to scientists the variety of conditions under which life can develop. For example, traces of bio or even technosignatures created by civilizations on various moons can provide a clearer picture of the signs for the development of intelligent life, thus building more prioritized paths for future missions to the most likely planets or moons for aliens to live on. But for now, we can only wait for the moment when we find the first exomoon and begin a long but life-changing scientific and technological ascent. Exomoons, despite their invisibility and skeptical insignificance, may one day critically change everything known to the entire human race about our vast universe. Even a small observation can eventually become the main driver for revolutionary discoveries. Continued research will reveal more and more answers, and only by pursuing this knowledge will the cumbersome, mysterious cosmos one day become less confusing to us. But in the face of the vast universe, we must never lose our enthusiasm for learning, no matter how difficult and distant our desired outcome.